Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is pressure relief valves. Our objective is to introduce both direct acting and pilot operated pressure relief valves and discuss their purpose, construction, and method of operation as applied to fluid power systems. The purpose of a pressure relief valve is to limit the maximum pressure by providing an alternate flow path to the tank when flow in the circuit is otherwise blocked. A pressure relief valve is an important safety device that prevents damage to the system and personnel. Given a fixed displacement pump rotating at a constant speed, flow rate produced by the pump is constant. When in the act of moving a fluid power actuator, flow has a place to go. If, however, the actuator has reached the limits of travel or flow is otherwise blocked by a change in valve position, flow has no place to go, and if the stupid pump keeps pumping and pumping and pumping, pressure rises and rises until a weak point in the system, ordinarily a hose or fitting, explodes. An alternative to this regrettable scenario is to purposely design a weak point in the system, known as a rupture or burst disc. The rupture disc is essentially a chintzy piece of metal that is designed to burst at a specific pressure, thus saving the system and any operators in the vicinity any damage. Ordinarily, the outflow of a rupture disc would be channeled via a drain passage back to the reservoir. Lacking this drain passage, a burst rupture disc would save the system from damage, however, spray fluid everywhere. While effective, rupture discs are inelegant one-time solutions to pressure relief, and more sophisticated methods are conveniently available, notably the pressure relief valve. The schematic symbol for a pressure relief valve indicates a pressurized P inlet port and a non-pressurized discharge port T. The P port on a pressure relief valve is ordinarily routed to a system under pressure, typically right next to the pump. The T port on a pressure relief valve is ordinarily routed to the tank or reservoir. Alternatively, these are also known as the primary and secondary ports of the pressure relief valve. The dashed pilot line indicates the pressure relief valve is sensing pressure on the pressurized P port. The arrow on the spring indicates the set value is user adjustable. The passageway linking P to T is normally closed, and at its deactivated state, the pressure relief valve does not allow fluid flow. When activated by pressure in excess of its set value, the pressure relief valve opens and allows fluid flow. When pressure drops to the reset level, the pressure relief valve returns to its deactivated closed state and stops fluid flow. Pressure relief valves are often referenced on a schematic using the shorthand RV, PRV, or if it needs to be explicitly stated that the relief valve is pilot operated, PORV. The purpose of a pressure relief valve, again, is to limit the system maximum pressure by providing an alternate flow path to the tank when flow in the circuit is otherwise blocked. Again, given a fixed displacement pump rotating at a constant speed, flow rate produced by the pump is constant. When in the act of moving an actuator, flow has a place to go. If, however, the actuator stalls out at the limits of travel, or if flow is otherwise blocked by a change in valve position, flow has no place to go. And if the stupid pump keeps pumping and pumping and pumping, pressure rises and rises until the pressure relief valve actuates and provides an alternate flow path to the tank, thus relieving pressure and saving the system and any nearby personnel damage. Consider the simplest of pressure relief valves, the direct-acting pressure relief valve. An extremely primitive direct-acting pressure relief valve can be created with a check valve employing a heavy biasing spring on the poppet. A check valve, if you'll recall, allows fluid flow in one direction, but blocks it in another. The heavy biasing spring modifier holds the poppet to the valve seat with a predetermined force. Given the orientation of the check valve, it would ordinarily allow free flow from the P to T ports. However, only does so when pressure-induced force on the poppet exceeds the force of the biasing spring. Even in the ordinarily free flow direction, the poppet remains seated at load-induced pressures below that sufficient to unseat it, and the direct-acting pressure relief valve remains closed. Only at pressures above that sufficient to unseat the poppet from the seat, the valve opens and provides a relief path for pressurized flow. Pressure in the system is therefore limited to a preset maximum. Alternatively, Consider this configuration of a direct acting pressure relief valve. In this configuration, a moving piston held down by biasing spring obstructs the main P to T passageway. However, a narrow pilot passageway acts on the bottom face of the moving piston. This pilot passageway is the dashed line in our schematic symbol. Given the pilot passageway senses pressure on the upstream P passageway, and Pascal's law states pressure in a confined fluid is exerted undiminished in all directions, pressurized input acts on the bottom face of the moving piston. When pressure-induced force on the bottom of the moving piston exceeds that of the biasing spring, the moving piston is forced upwards, opening a passage from P to T. Similar to our previously examined primitive pressure relief valve constructed with a check valve and biasing spring, at load-induced pressures below that sufficient to unseat the piston, the direct-acting pressure relief valve would remain closed. At pressures above that sufficient to unseat the piston, the direct-acting pressure relief valve opens, provides a relief path for pressurized flow. Pressure in this system is again limited to a preset maximum. The utility of this direct-acting pressure relief valve can be expanded by adding an adjustable knob. The knob's purpose is to change the force exerted by the biasing spring and therefore the pressure setting of the pressure relief valve. This is the spring and arrow modifier in our schematic symbol. Note that direct-acting pressure relief valves often employ a drain passage from the space occupied by the bias spring to tank. If any liquid leaked past the moving piston and filled this space, any accumulated liquid in this region would prevent the full movement of the piston and therefore prevent it from relieving pressure. For this reason, the drain passage keeps this space evacuated. Direct-acting pressure relief valves are simple constructions, and this simplicity is their inherent advantage over the comparatively more complicated pilot-operated pressure relief valve we've yet to discuss. There's not a lot of moving parts in a direct-acting pressure relief valve, and as a consequence, they're fast-acting, and there's not a lot that can go wrong. This simplicity, however, is as elegant as a wooden mallet. Not only are direct-acting pressure relief valves notoriously noisy, the principal drawback is their direct nature. Higher pressure systems necessitate larger, more powerful springs. Additionally, due to their simplicity of construction, the behavior of direct-acting pressure relief valves have something to be desired. In a perfect world, a pressure relief valve would have a clear and defined set pressure above which the pressure relief valve instantly and fully opens, and a reset value below which the valve instantly and fully closes. In the real world, this ideal behavior is far from the truth. Pressure often overshoots the initial set value, as this graph shows. To make matters worse, the regions operating at pressures near the set point, the valve, being directly acted upon by a spring whose compression non-linearly influences the actuation force, begins to open earlier than the valve's full open set value would suggest. Given a pressure relief valve, let's say an 800 psi set value, this means the P to T passage might begin cracking partially open at, let's say, 700 psi. Appropriately enough, this is called the cracking pressure of a pressure relief valve. The cracking pressure is the pressure at which a pressure relief valve just begins to open and is a value below that of the full open set value. Direct-acting pressure relief valves have a notoriously large difference between cracking pressures and full open pressures, upwards of 150 psi. Pilot-operated pressure relief valves, as we'll soon learn, not so much. In this case, the direct-acting pressure relief valve does fully open at 800 psi. However, operating at regions between 700 and 800 psi means a decreasing portion of flow is available to the system actuators, since an increasing portion is being dumped to the reservoir, as this graph shows. The difference between cracking and full open pressure is what may cause noticeable decrease in actuator speed as the system approaches the set pressure limit. The differential between cracking pressure and full open pressure is sometimes known as pressure override. In this case, our pressure relief valve has a pressure override of 100 psi. Cracking pressure is something that must be anticipated in a system and accounted for. If a system did truly need to operate at full flow capacity up to 800 psi, the pressure relief valve would have to be adjusted up to 900 psi to account for this valve's early cracking pressure and 100 psi pressure override region. This newer, higher pressure limit may, however, necessitate more robust components, fittings, and conductors. Note, preset, non-adjustable pressure relief valves exist without the adjustable knob. It is incumbent upon any technician employing these types of pressure relief valves to determine if the specified fixed pressure is the cracking pressure or the full open pressure. To account for these undesirable effects inherent in a direct-acting pressure relief valve, consider a pilot-operated pressure relief valve, sometimes called a compound two-stage pressure relief valve. The term pilot-operated is used in both hydraulic and electrical systems, and it kind of means the same thing. A pilot signal is anything characterized by low pressure, low flow rate, low voltage, or low current that controls the actuation of a larger primary device characterized by high pressure, high flow rate, high voltage, or high current. A pilot-operated pressure relief valve makes use of a low flow rate pilot signal to control the actuation of a larger flow rate primary valve. Pilot-operated pressure relief valves can operate at higher pressure and flow rates without the use of physically larger springs. In pressure override, the difference between cracking and full open pressure is considerably less. This does, however, come at a cost because pilot-operated pressure relief valves have a more complicated internal construction and operation. This being said, a pilot-operated pressure relief valve overcomes the principal disadvantage of direct-acting pressure relief valves in that pressure override, the region between cracking and full open pressures, is considerably less, often on the order of only 25 to 50 psi. This means a system employing the use of a pilot-operated pressure relief valve will notice considerably less diversion of fluid operating at regions near the pressure set point. A pilot-operated pressure relief valve therefore allows a more predictable response to a user-imposed pressure limit. Consider the internal construction of a balanced piston-style pilot-operated pressure relief valve. Let's ignore the V-port for now. We'll plug that and examine that in much later lectures. Note I've divided this pilot-operated pressure relief valve into pilot and primary sections. The primary section is a movable spool that closes the main passage from P to T. An orifice drilled through the main spool routes pressurized fluid from the primary P port to the pilot section. Note the orifice allows pressurized fluid on both sides of the main spool. Pressure is therefore equalized. Given equal area on both sides of the spool exposed to equal pressure, and your understanding of Pascal's law, is it any wonder that this type of pilot-operated pressure relief valve is known as a balanced piston-style pilot-operated pressure relief valve? The closure of the main primary passage from P to T is ensured by a light biasing spring that ever so slightly upsets the balance in favor of the closed position. As long as pressure remains balanced on both sides of the spool, the primary passage remains closed and pressure is not relieved. All it takes to upset this balance is a tiny push in the right direction as provided by the pilot section. Note the pilot section has a tiny movable dart and a small adjustable pilot spring. This dart and small pilot spring, quite similar to the behavior of a direct-acting pressure relief valve, is what maintains the balance of the balanced piston. Given this is the pilot section expected to accommodate low flow rates, and not the primary section expected to handle high flow rates, the bias pilot spring can be smaller and still be manually adjustable via the manual adjustment knob. Note the rear of the pilot chamber is at comparatively low tank pressure due to the drain passage. When pressure-induced force in the front of the pilot chamber exceeds the bias force of the pilot spring, the dart moves and upsets the balance of the balanced piston by opening the pilot chamber to tank pressure. The balanced piston is no longer balanced. The spool moves upwards and opens the main primary passage, thereby relieving pressure. Note only a small amount of pressurized flow is relieved via the pilot passage. The majority of the relief flow goes through the primary passage. The low flow pilot section therefore initiates the conduction of the high flow primary device. When pressure is dropped to the reset value, the bias spring reseats the pilot dart, pressure on both sides of the spool equalizes, and the light bias spring on the main spool ensures the primary passage remains sealed. The pressure relief valve is back in the deactivated closed state. Dig? Honestly, it took me a couple times to understand how a pilot-operated pressure relief valve works the first time someone showed it to me, so I don't blame you if you rewind and revisit the last section a couple times to make sure it sticks. Matter of fact, I'm going to make you revisit that last section again because I just know some of you think you have it, but you really don't. Here it is again without all the yammering. Fluid at pressure below the set value is conducted through the small orifice to both sides of the main spool. Given equal pressure on equal surface areas, the piston is balanced, and the added force of the bias spring holds the primary passage closed. When pressure in the pilot chamber reaches the set value, the pilot dart unseats and drains the pilot chamber to tank. The balanced pressure condition on both sides of the main spool is upset, and the primary passage opens, relieving pressure. When pressure drops to the reset value, the pilot dart reseats, and pressure equalizes on both sides of the main spool. The added force of the bias spring holds the primary passage closed. Long story short, you should understand that the pilot section's job is to simply tell the primary section when to relieve pressure by upsetting the balance of the ordinarily balanced piston. I don't know if this visualization exercise will help you understand the difference between a direct acting and a pilot-operated pressure relief valve, but even if it doesn't, try it, because it's super fun. You'll need your lab partner's help for this exercise, so you might have to go wake them up. I think they're asleep on the couch out in the hall with a half-eaten breakfast burrito on their chest. First, have your lab partner stand up, and then pick them up, and then toss them to the ground. This is how a direct acting pressure relief valve works. It takes some effort, but it gets the job done. Next, have your lab partner get up off the ground and push on you. Apply a token amount of resistance to get them committed to pushing you. And then just get out of the way and let them fall to the ground. Extra points if you guide their fall into a trash can or a chair. This is how a pilot-operated pressure relief valve works. It capitalizes on an active imbalance to accomplish what ordinarily only a great amount of effort can do if applied directly. Again, the principal advantage of all this complication is the fact that since the pilot section sensing the overpressure event isn't relieving primary flow, the spring could be substantially smaller and the relief event more precise. Pilot-operated pressure relief valves have noticeably smaller pressure override, which if you'll recall from like 3 minutes ago, is the difference between cracking pressure when the dart just starts moving and full open. A direct acting pressure relief valve might have a pressure override of 100 to 150 psi, whereas a pilot-operated pressure relief valve might have a pressure override of only 25 to 50 psi. Given the same pressure set point of let's say 800 psi, a direct acting pressure relief valve might have a cracking pressure of 650 to 700 psi, whereas a pilot-operated pressure relief valve might have a cracking pressure of maybe 750 to 775 psi. Actuators operating at regions near the pressure limit using the pilot-operated pressure relief valve wouldn't suffer lags in speed as they would with a direct acting pressure relief valve with noticeably larger pressure override. Alright, now that we've got a basic introduction to pressure relief valves, let's examine some basic scenarios involving troubleshooting. Since the purpose of a pressure relief valve is to limit maximum pressure for an entire system, they, quite like your lab partner, are often the culprit when things go wrong. Consider a system that fails to extend or retract a cylinder with the required amount of force. It might not be the cylinder's fault, but rather an improperly set pressure relief valve. Before you even think about taking anything apart, check to see if the pressure relief valve is set at the proper value and that no one has dorked with it in your absence. For this reason, the adjustment knob on pressure relief valves often feature a colored vernier scale on the stem. If you set it to green yesterday and you see gold today, you are justified in picking up your lab partner over your head and slamming them to the ground. Additionally, the adjustment knob on some pressure relief valves often must be pulled out or unlocked to make an adjustment. This prevents the set value from changing due to vibrations, especially in mobile hydraulic applications. Consider an improperly installed pressure relief valve with a blocked tank port. Can this pressure relief valve perform its required task? No. This is a bad situation. With a blocked tank port, the pressure relief valve cannot provide an alternate flow path, and pressure in the system will continue to rise until something bursts. Consider an improperly installed pressure relief valve with not a blocked tank port, but rather a severed connection to tank. Can this pressure relief valve perform its required task? Yes, kind of. However, this is still a pretty bad idea, because when the pressure relief valve relieves pressure, it's going to pee all over the place like a 5-year-old in a bathroom. The pressure relief valve does provide an alternate flow path, but it's not where you intend it to land. Let us now consider properly set and properly installed pressure relief valves and troubleshooting scenarios internal to their construction. Consider a contaminant in the fluid that happens to be in the wrong place at the wrong time and wedges itself between the pilot dart and seat. Can this pressure relief valve perform its required function? Think about it. In this case, pressure will be relieved. However, it'll be relieved a lot more frequently than you want. Recall that the function of the pilot section is to selectively maintain or upset the balance of the balanced piston. The contaminant has in effect introduced a leak in the pilot section that upsets the balance. Depending on the size of the contaminant and its malleability, the leak will vary in size. In this case, really the only thing that's ensuring the primary passage from P to T stays closed is the bias spring in the primary section. Once this low level of force is overcome, the balanced piston opens up and relieves flow earlier than expected. To make matters worse, the contaminant can become semi-permanently lodged in the pilot section. To make matters much worse, it could dislodge and rather than being flushed out, plug the drain port of the pilot section pending size. In this scenario, any incompressible liquid trapped in the pilot section resists movement of the dart, and the pressure relief valve is incapable of relieving pressure. Is it any wonder that fluid filtration and conditioning play such an important role in the safe and reliable operation of fluid power systems? For this reason, systems regularly filter fluid and often incorporate rupture or burst discs as last-ditch pressure relief mechanisms. Somewhat less nefarious, consider if a contaminant got semi-permanently lodged between the valve body and the primary spool. In this scenario, the pressure relief valve would constantly leak a small quantity of fluid, regardless of pressure, and actuator speed would slow, since a portion of provided flow is continuously diverted. A pressure relief valve exhibiting such a continuous leak might be warmer than expected. Both these scenarios involving contamination may warrant the removal and repair or outright replacement of the faulty pressure relief valve. Both scenarios could have been prevented with a proper level of filtration and regular maintenance. This really kind of wraps up the brief introduction of pressure relief valves I intended to accomplish this lecture. However, before we bring this lecture to a close, I'd like to make some brief comments on the wise use of pressure relief valves and the role of design and component selection in the efficient operation of fluid power systems. As essential as a pressure relief valve is for a properly functioning fluid power system, it is generally a good idea to avoid using it. This is to suggest that a properly designed system only infrequently goes to the trouble of building pressure to a certain level and then just dumping it to tank without accomplishing any work. The pressure relief valve in the act of relieving pressure is essentially wasting energy. Pressurized flow is converted to noise and a whole lot of heat, contributing to inefficiencies of the larger system. It would be far better practice to store energy or simply stop supplying it if your only option is to waste it. This is to suggest that a well-designed system doesn't regularly block pump flow, minimizes the time actuators are stalled to the limits of travel, and the fundamental realization that when you don't need flow, you don't need to pump. We'll discuss these and other interactions in later lectures on directional control valves, accumulators, and pumps. However, with your understanding of the content in the hydraulics math lecture available at the Big Bad Tech channel, it should be readily apparent that flow in units of volume per time, typically gallons per minute, is equal to displacement in units of volumes per revolution, typically cubic inches per revolution, times rotational speed in units of revolutions per minute. A system confronted with a scenario in which no flow is required has available two options that both serve to keep the pressure relief valve closed. 1. Use a clunky old-school motor that keeps rotational speed constant and decrease displacement per revolution with a clunky, leaky, complicated old-school variable displacement pump. Or 2. Use an inexpensive fixed displacement pump and an extremely sophisticated motor drive that simply stops spinning the pump when pressure gets too high. You can tell where my loyalties lie. Like I said in the Introduction to Fluid Power Systems lecture a while ago, a complete and thorough understanding of fluid power systems doesn't stop at the pump. but stretches into the motor driving the pump and well beyond. Problem is, we won't get anywhere if we chase every rabbit down every hole we encounter along the path. Other playlists at the Big Bad Tech channel discuss motors and motor controls, and it is well worth your time to check these out once you're done with hydraulics. You find it really is all connected, and as you gain more knowledge of more material, it's astoundingly easy to make the connections. Additionally, later lectures in the hydraulics playlist will discuss the mysterious vent port on the pilot-operated pressure relief valve for remote pressure sensing applications, other pressure control valves that reduce, modify, or monitor pressure in various branches of a fluid power system, as well as electrically controlled fluid power systems making use of pressure switches to regulate pressure. All this and more await. In conclusion, this lecture introduced the pressure relief valve, an essential fluid power component that limits maximum pressure by opening up and providing an alternate flow path to tank in the event fluid flow is blocked. We discussed the construction and operation of direct acting and pilot-operated pressure relief valves, and compared and contrasted their behavior with respect to pressure override. Finally, we discussed some basic troubleshooting scenarios involving pressure relief valves. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series.